In this video, we're going to talk about optimization problems. These types of problems have constraints that need to be satisfied. They have an objective function, and they have a quantity that needs to be either maximized or minimized. One thing that's going to help us in doing these types of problems is going to be the critical points theorem. And what it says is that if you only have one critical point, then it is the absolute maximum or minimum that you're looking for. One last thing about optimization problems is that they'll always ask the question, what is the maximum or minimum value of an objective function subject to the given constraints? So we're going to see this as we go through these problems. The other thing I want to mention is that I gave you a green handout that actually had the guidelines for optimization problems. So we're going to put them right here on page 85, and I'm going to read them to you so that you can see what we're going to be doing for these problems. The first thing is we're going to be reading the problems carefully and identifying the variables and to organize the given information, and a picture will be very helpful in these particular problems. Number two, our job will be to identify the objective function, and that is going to be a function that's going to be optimized, and we're going to write it in terms of our variables that we have for the problem. Number three, we're going to identify the constraints and write them in terms of the variables of the problem. And the one where I think most of the work for us is going to happen is going to be here for number 4, where we're going to use the constraint equation to eliminate all but one independent variable of the objective function. So we're going to practice that. Number 5, once we have the objective function expressed in terms of a single variable, then we're going to find the interval of interest for that variable. In other words, what values do we really want to look at? Number 6, we're going to use methods of calculus to find the absolute maximum and minimum value of the objective function in the interval of interest. And if necessary, we're going to check the endpoints. On page 86, we're going to do example number 1, which is the rancher's dilemma. A rancher has 400 feet of fencing for constructing a rectangular corral. One side of the corral will be formed by a barn and requires no fence. 3 exterior fences and 2 interior fences will partition the corral into 3 rectangular regions. And the question that we have is, what dimensions of the corral maximize the enclosed area, and what is the area of that corral? So the corral we're looking at is right here. Here's our barn, so we don't need anything. These are the 2 exterior and these are the 2 interior, and here's our long side. Notice that we want to maximize the enclosed area, so we know that our objective function is going to be about area. Before we get there, we're going to follow our steps for our guidelines. Number 1, it says to read the problem carefully and identify variables and organize the information given. We have a picture, so that kind of helps us organize it. But we're going to find that we're going to let x equal to the width of our rectangle, that's this part right here. And we're going to let y equal to the length of the rectangle, that's this part right here. And we already mentioned that we want to maximize our area, which is going to be our objective function. That's going to be area of my entire corral. That's going to be x times y. So that's what we have here. And notice we have 2 variables for that. We also need to go find our equation for our constraint. What we're going to find out for that is that we only have 400 feet of fencing. So of all the fencing that we need, we only have 400 to begin with. We need 4 X's, 2 exterior and 2 interior ones, all of the same size, plus that long side that's parallel to the barn. So these are our 2 equations. Notice both of them have X and Y. So step number 4 of our guidelines, the one we put an asterisk on, it says to use this constraint equation to eliminate all but one of the independent variables. In other words, we're going to solve for one of the variables. In particular, we're going to solve for y since it's already by itself. So here I am solving for y. y is equal to 400 minus 4x. I just subtracted the 4x to both sides. From here, we're going to substitute it into my objective function. So now you see that a is equal to x times 400 minus 4x. That's this part right here. We're going to get rid of parentheses by using the distributive property. And then in order to maximize the area, we're going to take the derivative. And that's how we're getting 400 minus 8x is equal to 0. Again, we also want to talk about our domain. We know x, we don't really want it to be 0, but we know it can't be more than 400 either. We can't have a negative x value. So we know that that's what we're looking at. Our number should be between 0 and 400. So I'm going to set this equal to 0, solve for x, and we find x is equal to 50. So that's going to be the dimension of this side right here. So we're going to plug that into our y equation. So here we are plugging it in. Y is equal to 400 minus 4. Instead of x, I'm going to put 50 and solve for y. Y is 200. Remember, x comma y is our point, our critical point. Since we only have one critical point, we're going to assume that that is our maximum. So they wanted us to find the dimensions to maximize the area, and we found that to be 50 feet by 200 feet. And maximum area is 10,000 square feet.